Okay, hi Chem 30. I'm going to do one lesson today. This is slide 34 in my notes. So these are review of rules for naming alkenes and alkynes and where you number them from. So take a look back at my last lecture to reinforce these examples. I've done a ton of those examples in your assignment. So this nomenclature, kind of work project, I've done a bunch of those examples. I did a bunch the other day in the lesson. I'm going to come back to actually, I'm not going to come back to this today. I don't think there's no benzene in here. So I'm actually not going to touch on this a ton today. But you have tons of examples here, naming alkenes and alkynes. I'm going to move on from that. I'm going to introduce different types of reactions. I'm going to talk about refining today, and we're going to talk about benzene. Okay? So these are, remember what aliphatic means? So aliphatic means no benzene. This could be a cyclomolecule or a straight chain. So aliphatic hydrocarbons have no aroma because they have no benzene. So these are main examples that, now look back in your textbook for main reactions of aliphatic hydrocarbons. There's a summary of all the reactions on page 379. So take a look at that. Aromatics start on page 381, which is benzene, and that's where I'm going to address new material today. I'm going to put a little table up on. I'm going to put a little table up on the board here. I'm looking for a specific page. Page 386 is going to be an important one today, looking at oil refining. Okay, so you have combustion reactions, obviously, with aliphatic hydrocarbons, and that's any hydrocarbon plus oxygen, right, which makes water plus carbon dioxide, right? Now that's complete combustion. I am going to talk a little bit about incomplete combustion today, where it's not just water and carbon dioxide built. You also have carbon monoxide or elemental carbon when things don't burn cleanly. I'll talk about that a bit more later. Hydrogenation is another reaction. So I'm just introducing these in the lesson today. We're going to go through them in more detail as we get into different types of polymerization. So this is hydrogenation. So addition of hydrogen. So here's an example. You take an alkene, you add hydrogen, and then this makes an alkane. So you go from an unsaturated hydrocarbon, you add hydrogen to a saturated hydrocarbon. Okay? So here's an example. So add hydrogen. This is a complete structural diagram for everything. All right, so here's an example of hydrogenation. where we take butene or but1ene, add H2, and turn it into butane. Okay? I'm going to talk about this a bit more in a few more slides. Cracking is another thing that we'll talk about. You need to know the difference between cracking and ethane cracking though. Okay? So cracking is a process in which much larger hydrocarbons are broken down at high temperatures. So think breaking down large hydrocarbons like bitumen from the oil sands. I'm going to talk about oil sands production a bit more today. Breaking up those big hydrocarbon molecules. Bitumen's actually about 40 different hydrocarbons. And when we crack it, we actually centrifuge it with heat and catalysts and break them into smaller component parts to remove impurities and then start to siphon off the different components to different types of pipeline products. Ethane cracking is different from this. Okay? It's specific. We change ethane, all right, so a component of natural gas, into ethene. So ethane cracking is specific to this process. And the reason why it's specific is because we use ethene as a monomer, as a single unit, okay, to make all of the plastics that we use, all right? So ethene is the basis for all plastics. It's called ethylene or vinyl, all right? And again, we'll talk about when we talk more about polymerization and building large molecules like plastics, but you should know the difference between cracking and ethane cracking. All right, so here's an example of cracking. All right, so again, cracking is a process in which larger hydrocarbons are broken down at high temperatures and with catalysts to produce smaller hydrocarbons. So pentane plus heat, right? I could crack this into ethane and propane. Right, so C5H12 plus plus thermal heat makes C2H6 plus C3H8. All right, so if I'm going to extract natural gas, I could take the larger hydrocarbon, crack it into two smaller, more useful gases, right? Propane obviously used for barbecues, and ethane is a component of natural gas in things like natural gas engines, right? Okay, and ethane cracking, just to show you what it looks like. I'm going to take C2H6. So I can crack a larger hydrocarbon, turn it into ethane, and then ethane crack, which is generally how ethene is made. Okay, so plus heat, and this is going to make C2H4 plus heat, and then plus H2. Right, so I'm going to take the ethane. I'm just going to use a skeleton equation here. Use heat and possibly other catalysts to make ethene. Plus H2. Okay. So this is an industrial term to make ethylene. So this is this is ethene. We also call it ethylene. And it's the base unit for modern plastics. And I'm going to talk about a bunch of different types of plastics that we use. So this comes from natural gas. Okay? So I'm going to give you a little table here, and you need to know this. Okay, so reaction, reactants, and products. I'm just going to summarize what I just talked about. So combustion, right? You have any hydrocarbon and oxygen. And if it's complete combustion, H2O and CO2 are the products. In hydrogenation, you'll have an alkene or an alkyne, and I'm going to take the double and triple bonds and I'm going to break those up into single bonds. Right? I'm going to add hydrogen to the alkene or the alkyne and turn unsaturated hydrocarbons into saturated hydrocarbons. So I get an alkane from that. Cracking, I'm going to take an alkane and I'm going to have heat and catalysts, and this will typically be a longer chain. I should write that. And then this makes multiple shorter alkanes. Okay, so combustion, hydrogenation, and cracking. And the last major reaction that I'm going to discuss today is ethane cracking. So you take an alkane, use a heat or a catalyst, and you're going to make alkenes and alkynes and hydrogen. And I should put hydrogen here as a product as well. But your biggest one's going to be ethene. Okay, or ethylene. I could also make polyethylene, but this is the most common thing that's cracked in this way to make plastic derivatives, and that's why it's called ethane cracking. Okay, another thing, so just so we look at, okay, so those, just to go back here, those are your four main reactions that will be of interest today. Adding to this, you should also understand the difference between some configurations with these molecules. So if you look at, I talked about how double and triple bonds, the double and the triple bonds are easier to break up and metabolize because they have spaces between them, right? So that double or triple bond makes kinks in the molecule. So this is an unsaturated, these are unsaturated hydrocarbons, right? So when we talk about fats or lipids that we intake in our diet, this is an unsaturated fat, and it could be an unsaturated fatty acid that we mostly get from plant resources, right? This is why plant fats tend to be healthier, because they have these unsaturated bonds, and as a result, the molecule itself, its carbon backbone is spaced apart. So it's easier to break down and it's easier to digest. Okay? So that's why we should have a lot of healthy plant fats in our diet. We do need to have saturated animal fats in some aspects, but if we can limit that, that means that we have less of these dense fats that get deposited, on our arteries or build up excessive amounts of fat stores in our body. Okay, so here's the deal with these. These are unsaturated hydrocarbons. They're isomers. Now, where the double bond is, this molecule has hydrogens on the same side, so on the same orientation. So this is called a cis, right? This is called a cis molecule. This would be a cis fat or a cis fatty acid. Right here, you actually see the hydrogens at the double bond. Right between these two carbons here, there's a double bond, but the hydrogens that they have accompanied with them are across the bond, and this is called a trans fat, or a trans configuration of hydrogens at a double bond. So these are isomers. So they'll have the same chemical formula, but the rotation of the molecule is restricted because of placement of double and triple bonds. So cis molecules have their carbon chain oriented on the same side of the double or triple bond, and trans molecules have their carbon chain oriented across the double or triple bond. So, we talk about trans fats and fast foods and things like that. The reason why this is important, all fats that exist in nature that we consume, all of them are cis molecules. Okay, so they're all cis. You've probably seen cis and trans talking about gender, right? Right, an individual who is cisgendered would have conventional genitalia and gender assignments that society would normally think of, right? Whereas an individual is transgendered is someone who doesn't fits those norms. All right. And cis and trans exist naturally along biological lines, right? So you've seen these terms before. So that's what it means. Trans means across. So in this case, this means across a double bond, or having components of both sides of a molecule in this context. All right. So when you look at the thing is about this is all unsaturated fats on Earth that exist naturally, all of them have cis configurations. So anything that we would eat normally. Now synthetic fats, things that we actually fortify in fast foods, some of them have trans fat bonds. So they don't exist naturally at all. All right? And this is the issue with trans fats, is that we have no enzymes to digest them. So all they do is get deposited as liver fat and then cause scarring on the liver, much like alcohol does to cause cirrhosis. So this is how trans fats are produced. And again, you're never going to see them exist in nature. All right? So a lot of fast food industry, now they're cheap, that's why we use them, because it comes from canola oil. So here's what happens with the hydrogenation process of trans fats. So we take unsaturated fats and put the vegetable oil or canola oil into a heater with a nickel catalyst and then hammer it with hydrogen gas. All right, so you pump hydrogen gas onto the unsaturated fats to saturate them. And then what happens is you end up with hydrogens on either side of a double bond. So they act like saturated fats, but they're unsaturated, and the hydrogen configuration is nothing that the biological system recognizes in nature. So we don't have enzymes to break it down. The trans fats just end up getting deposited in our body or pass through our digestive tract and cause things like indigestion. Right? So here's the deal with trans fats, is they're harmful because they're unnatural, right? They react in strange ways in the body. They mimic the effects of saturated fats because they remove that kinking. All right? And we're supposed to limit our daily intake of saturated fats. So trans fatty acids are an industrial produced fat. So what we do is we take canola and we hydrogenate it, and that creates margarine, right? And then we further hydrogenate it to turn it into an industrial grade fat that you would see in a fast food deep fryer or something like that. All right. So if you're talking about sort of like the age-old discussion about which one's healthier, butter or margarine, right? Butter comes from animal sources, and margarine comes from hydrogenated canola. Because margarine's full of trans fatty acids, the butter is healthier for you, right? So if you're going to do the crime with the fat, then you do it right. It's kind of like drinking Diet Coke, right? There's no sugar, but it's still poisonous. All right. Trans versus cis. Those are our main molecules. The next piece I'm going to talk about here is aromatics. So we've been talking about aliphatic hydrocarbons since we've started this unit. Aromatics are any compound that contains benzene. Now, benzene is C6H6. I'm going to show you what it looks like. So all bonds in benzene are identical. There's 6 unbonded valence electrons that are said to be delocalized. This is what makes benzene special. And this phenomenon is called resonance, and I'm going to explain that here. So these are benzene rings, all right? So you're likely going to see benzene most commonly like this. So this circle indicates benzene. So it's a cyclohexane molecule, but what's special about this is it has alternating single and double bonds. Okay, so when I see benzene, you're gonna see it like this. You'll see it with alternating double and triple bonds. That's kind of like the line structural formula, but benzene is actually best represented like this. And this shows resonance because this shows sharing of electrons. So when if I draw a complete structural diagram for this, the benzene ring looks like this. Okay, so there's one hydrogen attached to each carbon. Alternating double and single bonds, right? So all of these are carbons. And then you got a single bond, double bond, single bond, double bond, and it alternates. Now, because of the quantum nature of this alternating double and triple bonds, it turns out the electrons are like an ideal space away from each carbon atom. And because of that, the electrons themselves aren't owned by any of these single carbon backbone molecules. They kind of drift and shift between the orbitals of all of these carbons, okay? Now remember, when we look at the quantum model of the atom, and we look at the nucleus, right, we don't actually really have, like this is your typical Bohr-Rutherford model, but we don't actually have these defined orbits, right? What we have is electron clouds, right? So spheres of electron clouds. So we have electron clouds that have different spaces and strengths. So spaces, strengths, and electron spins are unique to each of them. Now electron spin is also a really mysterious movement, and we don't really have, it's unlike anything that you see in everyday nature, all right? Because when we're talking about spin, we're talking about a quantum mechanical phenomenon, and we can't observe quantum mechanics like in our daily life, so we don't actually have good language for this because I can't see electron spin, and I don't. We feel the effects of it through things like electricity and magnetism, and through the way molecules work, but I can't observe its nature because quantum mechanics is so small. All right, we're talking about really, really small phenomenon here, right? But we know that electron spin happens because we can predict it. And it happens very predictably. So think about an electron itself. I mean, an electron is not really a molecule. It's a probability that exists in space, right? So it's a probability of energy charge. And the electron, as it spins, it has this like attractive beacon. So think of an electron, if we're talking about the particle nature, think about an electron as like a moving lighthouse. And then the light kind of moves around, and that's actually the negative charge. So the negative sphere of influence is constantly sort of rotating around this electron. And when you look at electrons, right, electrons can spin one direction or the other direction. So this is actually how I would represent electrons and electron orbitals. So one's oriented in one direction, one's oriented in the other direction. And their spins are perpendicular of each other. And the electron spin is actually what creates magnetism. Okay? So not only are they distanced, right? Not only are they distanced an ideal distance away because of the alternating single and double bonds, their spins are aligned in a way that gives these molecules very, very strong stability. Okay? So the electrons are shared equally among the carbon atoms, and this makes benzene extremely unique. And this phenomenon of the interlocking sharing, I guess the interlocking relationships of the electrons being shared with all these carbon atoms at once is called resonance. Okay? So you know resonance in the form of sound, right? When you have overlapping sound waves, and then the overlapping sound waves give you the illusion that something's louder than it actually is, just because the waves are interchanging. Think of it kind of like that, where the overall effect of the electron is exclamated with the sharing of it. All right. So this, is based on quantum mechanical properties. But benzene is a very, very stable molecule, and it's really useful as a result. Okay? So, like I said, you're going to see benzene mostly like this. This contributes to the stability, so the extra electrons being shared by all the carbons. The electrons are delocalized, and I can't really draw a Lewis diagram for it because the electrons they're not associated with any single carbon. They're floating in between the electron clouds created. Okay? I'm going to write, just 1 second here. So I'm going to go back to the other slides, but I want you to take a look at this. So the main properties of benzene that make it unique. So its chemical formula is C6H6. All the dipoles cancel out in benzene, so it's nonpolar. It's actually unreactive with hydrogen. All carbon and carbon bonds are the same length. And this has to do with the spacing in a quantum field with the carbon atoms. All carbons are identical and are bonded to one hydrogen. Now, the most important piece of benzene and why it's really useful for humans is that it's highly stable and it's unreactive. Like alkanes, it behaves like a saturated hydrocarbon. And as a result, because it behaves like a saturated hydrocarbon, it's really hard to clean up. All right? And it adds to the strength and stability and weight of hydrocarbon molecules. So bitumen has a ton of aromatics in it, so lots of benzene. So that's why bitumen itself, so that's the main hydrocarbon we pull out of the oil sands. It's the most dense hydrocarbon that we use in an industrial in an industrial fashion. So bitumen's unique among all other types of oils because it actually sinks in water, right? So that's a big deal if a pipeline breaks, right? If a pipeline bursts, that bitumen doesn't float, so it's really hard to clean up. So you're essentially not cleaning it up, right? So if a pipeline bursts, which is like what happened in Minnesota a few years ago, a pipeline from Hardisty that was part of the Enbridge Line 3 broke and threw bitumen into the Missouri River, and that you can't clean that up because it sinks unless you dredge the bottom. So that's why there's so much opposition to things like bitumen pipelines. All right, not only for climate change reasons and people protesting things that they don't really know much about, but one of the big main concerns, and it's a legitimate concern, is that bitumen sinks. So how do we clean it up if or when it bursts, right? Okay, so just keep that in mind as we go along, okay? So benzene has lots of different types of derivatives. So aromatics are also called phenolic or phenyl compounds. I'm going to talk about how or why we call something benzene and how we call something phenolic or phenyl. Aromatics occur naturally in petroleum-based resources. We put benzene into octane or gasoline because it stabilizes the fuel, so its flash point is a bit lower in case of a spark. It helps things burn cleaner because you need a higher temperature to burn a heavier hydrocarbon, and gasoline doesn't smell, right? So if we don't put benzene into the octane, then we won't smell it. We don't know that it's a hydrocarbon, right? Because gasoline looks like water. All right? So benzene is a stable compound because of its structure. All right? Here's the deal with benzene. Benzene looks like, so when we look at DNA, this is why you shouldn't huff gas, by the way. So when we look at DNA is made of a sugar phosphate backbone, and then you have a nucleotide attached to it. And then you have, on the other side, right, DNA is double-stranded. You have a pentose sugar. So you have a 5-carbon sugar, and one's right side up and one's upside down. Now here's the deal with benzene. This benzene molecule looks a lot like the pentane molecule. So the benzene itself can insert into your DNA. All right. So if I'm exposed to a lot of benzene molecules, benzene can insert itself. That's called a chemical mutagen. It can insert itself into your sugar phosphate backbone of your DNA, and then that causes mutation, right? Which is why benzene is toxic, right? So it can be carcinogenic or lead to other types of issues. All right. So benzene, because of its stability as well, it doesn't break down. So organic compounds that are resistant to being broken down by biological or chemical means are called POPs, or persistent organic pollutants. So benzene has the ability to bioaccumulate up a food chain, right? So, and I'm going to talk about a bunch of different benzene-derived molecules that do this. Now, benzene does not dissolve in water, right? It's a fat-based molecule. So these persistent organic pollutants, because they're industrially processed, okay, they themselves don't have natural chemicals or bacteria or viruses, things like that, that break it down in a natural environment, right? And they dissolve in fat, so they can bioaccumulate in the fat stores of animals. So cleaning up these types of molecules are called remediation, and we're trying to do things like genetically engineer bacteria to be able to naturally break that stuff down, okay, or any benzene-based molecules. You can have multiple molecules that have multiple benzene rings, and these are called polycyclic aromatic hydrocarbons. And all PAHs are POPs. All PAHs are persistent organic pollutants. So there's a good film about what happened with DuPont in West Virginia about 25 years ago. It's called Dark Waters, and it's about benzene-based molecules. It would be worth a watch. It's about Teflon. All right, and the consequences of having polycyclic aromatic hydrocarbons in natural environments. So polycyclic aromatic hydrocarbons are compounds that contain multiple benzene rings. They're produced by incomplete combustion of organic molecules. So when there's not enough oxygen, oils, fossil fuels, wood, garbage, plastics, they'll all make PAHs. And again, these can act as chemical mutagens, much like any mutagen of DNA, and they can insert themselves into the DNA structure. So a few of these things, pyrene is flame retardant. This used to be on all of our furniture before we realized it did things like cause DNA mutation and stillbirths. Naphthalene are these are mothballs. So you've probably smelled those before. And quite a few of these other things are pesticides and herbicides. All right. So here's some other common benzene molecules. Toluene, so glue. Xylene is rubber cement. Other types of benzene molecules that you'll see: vanilla, or vanillin, the molecule that gives vanilla its flavor. Acetylsalicylic acid is aspirin. Okay.